Okay, so in the last lecture, last time, I introduced you guys to the notion of a homology. So, homologies. Alright. So, the basic idea of homology, so at its very core, or at least at the very foundation, or at the very start of when you guys learn what homologies are, the basic idea is to embed a simplex, an n simplex, into our space X, and then from there compute homologies of those embedded simplices in our space X. So I didn't mention this in the last lecture, but that notion is actually called a simplicial homology. So we discussed about simplicial homologies, and I forgot to actually write the actual notation for it. It's hk delta of X. And I also gave you guys a taste of a much more general way of constructing homologies, which is by coefficient groups. So if I have my homology group hk of X, I can express each of the elements of the homologies as linear combinations, right? Linear combinations of certain stuff, or algebraic forms, or not really algebraic forms, but algebraic interpretations of the embedded simplices in X with respect to a given coefficient group. And the coefficient group is an abelian group with respect to addition or multiplication, but mostly addition, because it's cleaner. So our coefficient group is G. And so what I didn't mention in the last lecture is that G can be any abelian group you guys can think of. I think I mentioned that, but I just want to make it clear here. This can be R, so the addition, the real numbers with addition. Of course, Z plus, which is the trivial way that we express G as. We can even think of it as the complex numbers with addition. That's the same thing. And if you want to get crazy, you guys can express it in terms of the quaternions with addition. It can also be the octonions with respect to addition. So let me just write that blackboard boldface O properly. It can even be, what else? Not only O, but also maybe even the sedenions. Though I don't think there's a notion of addition there, but the point is it can be any abelian group you guys can think of. Even if it can even be ZP for P prime. So it can be a subgroup of Z plus. And as you guys all know, subgroups of abelian groups are also abelian. So there's that. And of course, don't forget the usual standard Femboyization of our homology groups. So hk of X. And our simplicial homology. So that's the same thing. All right, so that was the last lecture. And we also did sample computations of homology. So we tried to compute the homologies of a graph with one edge and two vertices. We interpreted that as embedding two copies of a zero cell. So these are zero cells, and then one copy of a one cell. And so we tried to compute the homologies from there. And so after that, we also tried to compute the homologies of S1, which is the unit sphere in C. And it doesn't matter which space S1 lives in. It can live in R2 or C. It doesn't matter, because C and R2 are isomorphic. So it doesn't matter. All right, so there's S1. We interpreted as we embedded one cell in it and one zero cell in it. And we found that the simplicial homology of S1 with respect to Z coefficients is, well, it's isomorphic to the singular homology of S1, which I will show you guys later, with Z coefficients. And this is just defined piecewise via Z for k equals 0 and 1, and 0, or it's trivial, for k greater than or equal to 2. So that's what we computed last time. So in this lecture, we're just going to be continuing those computations, and we're going to bump up the complexity a bit by considering a torus. Or before we get into the torus, let's first consider another graph and see. Let's try to generate a procedure for trying to find homologies for graphs in general. Okay, so let's consider so let's consider a bunch of 1 cells and 2 cells. So it's another graph. So I'm gonna use red to denote the vertices, and then black for the edges. Connect these guys together. All right, so I want to find the homology of this guy. So notice how I'm not putting a 2 cell over here. It's just a bunch of 1 cells. It's a strictly one-dimensional object. So it's a strictly topologically one-dimensional space. So you guys can of course think of this as a continuous line of femboys strung together, or with breaks, and then those breaks are a bunch of distinct femboys, and then those guys are the red vertices over here. So you guys can think of embedding just one cell, but that's actually pretty hard. So what we're gonna do, so that you guys can get into the details of computation, is I'm gonna think of embedding 3 1 cells into here and 3 0 cells, of course. So first things first, when it comes to these things, is I'm gonna pick an orientation. Now you guys will see that orientation doesn't matter. You guys can orient it. I'm orienting it here counterclockwise. You guys can orient it clockwise. It doesn't matter because these things are abelian anyway. But I'm gonna pick this orientation just for the sake of it. Okay. So once I pick an orientation, of course, I want to label these vertices. So let's label it X, Y, Z. And then I'm going to label the edges A, B, and C. Okay. So, of course, our chains, okay, so in our chain complex, so our Cn, I forgot to mention this in the last lecture, and I'm deeply sorry for that. N minus 1, and then N minus 2, and then on and on. And then I have my del N minus 2, del N minus 1, del N, del N plus 1. So in a chain complex, which we construct for our, for our complex, or for our cell complex at least, because we're talking about, embedding a bunch of cells to sort of approximate, quote unquote, approximate our space, because we can't just find the entire homology of a space, right? Because it's too continuous, it's not discrete, and then, it's like I don't think I mentioned this in the last lecture, but I think, in my opinion, this is a sort of topology application of Lebesgue or Lebesgue measures, because Lebesgue measures are like, we try to approximate an area, we try to approximate a measure of something by fitting it with a bunch of squares or hypercubes, right? And then we find the measures of those hypercubes, and then a rough sum of those, it's sort of the limit or the supremum, the infimum at least, of a certain set of a sum of measures of cubes, right, or hypercubes. And then we use that to approximate the actual measure of a set, right? So here, what we're doing is we're trying to approximate the homology of a group, right? We're trying to approximate the topology of a group by using triangles, or trying to use cells in approximating it, or in finding the homology, of course. All right, so going back here, in our complex, each of these abelian groups are called chains. All right, so these are chains. So in this case, Cn is an N chain. So N chain. Cn to the minus 1 is an N minus 1 chain. N minus 2 is an N minus 2 chain. N minus 2 chain. And so on and so forth. So if I have C0, if I have C3, C2, C1, C3 is 3 chains, 2, and then C2 is 2 chains, on and on. And you guys will get the terminology here. Right? It's based on the dimension of the cells or the simplices you embed inside there. And the group itself, or the abelian group itself associated with your space, that N chain is associated or is spanned or generated by how many, or all those possible n-dimensional things, or cells or simplices you put in your space, right? So if I have 3 simplices, or if I have 3 1 simplices in my space, or 3 1 cells, that means I would have an abelian group that's generated by 3 objects. And likewise, since in my space here I have 3 0 cells, that means my 0 chain is spanned, or at least is generated by 3 elements. So you guys can probably see it by now. And you know, because I don't have a 2 cell here, my 2 chain is trivial. So we start at 0, del 2, and then the C1 is the free abelian group generated by ABC, the edges ABC, and then C0 is the free abelian group generated by XYZ. So all permutations of those guys, or linear combinations of those guys, with respect to coefficients in the integers right now. So you guys can think of coefficients in the real numbers, or as I said, in those other abelian groups, but right now we're just going to consider the integers because it's much cleaner. Or you guys, I can just say, okay, in coefficients in G any abelian group, so you guys don't get your knots tied up. All right. So del 2 would take the trivial group to C1, which is the final the free abelian group generated by the edges ABC, and then that that free abelian group is sent to XYZ. So ABC are a continuous line of femboys, and then XYZ is our, you know, 3 discrete femboys where those 3 fine lines of femboys terminate at. So how I'd like to interpret this is that these free abelian groups are more of the interactions these guys can make with each other. These femboys can make with each other. Some abstract interaction they can do with each other, like talking to each other or other things. So that's how I like to interpret it. So this is my del 0, and of course it maps onto 0. And right off the bat, you guys already know del 2 is the same as del 0, and then the image is just 0 throughout, because there's nothing else we can do with the 0 femboy. Alright, so you guys can notice that this is immediately the same as Z3, and then that's mapped to Z3, and then that's mapped to 0. Or using my terminology of my coefficient groups, G direct sum, G direct sum, G, and that's mapped to the same thing, G direct sum, G direct sum, G, and then that's mapped to 0. Now the reason why I wrote that in terms of direct sums is that we don't know what exactly is the structure of the group when we actually do take the direct sum. Like for example, if I take the direct sum of the complex numbers with itself, I wouldn't necessarily get C2, right? And C2 is, you know, if I want to replace C2 with, let's say, the real numbers or tuples of the real numbers, I cannot just say R2 because those are not isomorphic. C2 is a 4-dimensional space in the complex numbers, while R2 is strictly a 2-dimensional space. So really it's best to just write it in terms of the direct sum if we're talking generally about coefficient groups. But if I'm gonna say G is the integers, then I would most definitely write it as just Z3, right? Just so that it's not confusing, and you guys can work out all the kinks or the confusing stuff when you plug in the coefficient group that you want to plug in. All right, so there's del 2, there's del 1, there's del 0, and we know that del 2, or the image of del 2, is the same as the image of del 0, which is just 0, according to our exact sequence. All right, so let's find out, or let's compute the boundary maps. Of course, it's immediate for each of these edges, according to my orientation, that it's terminal vertex minus initial vertex, right? So that's a fundamental fact I mentioned in the last lecture. So it's immediate that the del of A is y minus x. According to our orientation, del of B is z minus y, z minus y. Del of C is x minus z. And of course, the span of all these guys generate a free abelian group that's of 3 generators. Okay, so now that we know the maps of that, I suppose we could try to find the kernel. Right. So the kernel. No, okay, that's it pretty much. Yeah. Yeah. All right. So let's try to compute the zeroth homology group of our space X. I didn't label this, so this is our space X. But you guys already know it at this point. So our homology group H0 of X is of course Z0 mod bound 0. So the kernel of the the del 0 mod the image of del 1. Now the kernel of del 0 is basically everything that's sent to the trivial group. That's just G direct sum G direct sum G. Mod the image of del 1. The image of del 1 is the finite I keep saying finite. The free abelian group generated by these images. So it is, you know, del of A. I'm not gonna write the full, you know, x minus z, y minus z, something like that. Okay, no, I'm not gonna write that anymore. Del of B and del of C, wherein, you know, it's those things in the box. And you notice that these guys, or this free abelian group, is just the free abelian group on 3 generators, and it is precisely isomorphic to G direct sum G direct sum G. And that's just isomorphic to that G direct sum. So it's basically just direct sum itself, right? And you already know from last lecture that that is trivial. And it's a bit weird or paradoxical how this is trivial, because you guys will notice that this here is a connected space. This is connected. This is of only one path component. Yet it has 0 for homology group. So this is our only counterexample to the fact that for any path connected space, the 0th homology group is precisely our coefficient group, G. But in this case, we've shown that the 0th homology group of this particular path connected space is actually just trivial. So watch those. So watch the computation of your 0th homology group. All right. So let's now compute the first homology group. So you guys will probably think that this must be G, because we have one hole inside it. So it's trivial already, but let's still get into it. So H1 of X is the kernel of del 1 mod the image of del 0. So cycles mod boundaries. Alright. So the kernel of del 1 is whatever is sent to 0 in the free abelian group generated by X, Y, Z. So the kernel of del 1 I would like to think of as a linear combination of A, B, and C, such that it would be equal to 0. So I'm thinking of numbers L times A plus L times B. Oh no, I'm gonna pick a different letter. M times B plus N times C, which is equal to 0. So that's what we mean by kernel. So I'm gonna expand this out. So A, recall, is mapped onto Y minus X. B is mapped onto, because we're talking about the image that equals 0, right? So we're talking about, so the image would have to be 0 in order for these to be part of the kernel, because we're trying to look for the kernel of that map, or the homomorphism. Okay, so M of Z minus Y, because B is mapped onto Z minus Y, and then N times C is mapped onto X minus Z. And all that's equal to 0. So expanding things out and then, you know, gathering up the common factors, I would have N minus L times X plus L minus M is Y plus M minus N times Z is equal to 0. So in this case, right now we have a free abelian group which is given by this relation between its generators. Wherein, of course, N, L, and M are elements in G. Okay, our coefficient group. So right now, this relation will only work, right? It will only work when all of these guys are equal to each other. So N is equal to L is equal to M. So right now, we have a free abelian group generated by this over here. So what we want to do is mod out by that equivalence. So what we're looking for, so the kernel would be this here. So it would be this entire expression. So I'm just going to write here, but it's underlined and you guys get it. Mod the relation that N equals L equals M. And then when that's the case, we essentially treat N, L, and M as a singular point, which is just one sort of element. And then we end up with a free abelian group generated by X plus Y plus Z. And that's just isomorphic to one copy of our coefficient group. Okay, so now we found the kernel. Let's just plug that right here. X plus Y plus Z. And then mod out. Alright, so what's the image of del 0? The image of del 0 is just the trivial group. And then you guys will find that it is X plus Y plus Z. And that's just isomorphic to that, I suppose. Let's write that more concisely. Okay, and then that is just isomorphic to my coefficient group G. So in general, and okay, let's how about H2 of X? So what's our second homology group? So that second homology group and the higher homology groups vanish because of course it's 0. We don't have any 2 cells in here. We don't have 3 cells in here. Or we don't have 2 simplices. We don't have 3 simplices here. So it doesn't, that's nothing. It just all vanishes. So in general, HK of X, so our homology of our space X is precisely G for K equals 1 and 0 for K not equal 1. And of course, our Femboyized version. So F HK of X is FG for K equals 1 and the trivial Femboy group for K not equal to 1. Not equal to 1, not 0. Okay. So that's another trivial example. So let's bump the complexity up a bit and let's consider the homology group of a torus. So FT2. So we've discussed about the fundamental group or the first homotopy group of a torus, but now let's actually, and you know, we employed some heavy machinery on trying to compute that thing, that invariant or that thing that distinguishes it from other spaces. But now let's try a much more simpler and humble approach to distinguishing the Femboy torus from other Femboy structures, such as the Femboy sphere, Femboy ball. But little side note, Femboy balls are contractible. So that means I can deformation retract them to a single point, and so its homologies would just be isomorphic to a point, so a single Femboy. So yeah, there's not much to talk about when it comes to solid spaces like a solid torus S1 or FS1 cross F. You know, a thigh and a one thigh cross a one prosciutto or a two prosciutto, right? And you know that those kind of spaces are trivial because I can just deformation retract them to a point. So yeah, there's that. So we're strictly considering hollow spaces. We want to do that because they're much more interesting and they hold, they're not easily deformation retractable to a singular point. So, right. So I discussed in the last lecture that what I can do is, wait, I think I already discussed this, didn't I? Yeah, I think I already discussed this. I'm so bad at memory. Yeah, I think I already discussed this. Did I? Or maybe I just mentioned it as a sort of thing. Let me just check my stuff. Yeah, I didn't. I just mentioned it as a small thing. All right, so let's do this. Okay, so on the one hand, I can try to do a simplicial homology using simplices by triangulating the space by putting a bunch of tiny little triangles on it, tiny little 2 cells, and then computing the homologies from there. But that would be a long and tedious process. So what we're going to do is consider its identification space. So let's consider FT2. So the Femboy donut. Okay. So I have my identification space. And then I'm gonna write my identification arrows with different colors. And then, all right, to make things simpler, I'm gonna draw a line, a diagonal line going from this edge to this edge. And I'm gonna orient it, I'm gonna color it blue, but note that this is for orientation, not for the sake of identification, all right? So I'm gonna orient it this way. So that you'll notice that when I try to follow the flow of this, it goes round like this. So that's what we define by a cycle. It's a loose definition of a cycle. And then notice that if I go this way, it sort of goes along with the flow. Okay. So, and then next, because it's not just a wireframe thing, right, we have surface. This time, there are 2 cells here. So these here are 2 cells. So what we have are embeddings of 2 cells, 1, 2, 3, 4, 5, 6 1 cells, and 4 0 cells. But here's the thing, here's the crucial observation that makes our computation much easier, right? And this time we're not gonna be talking about cellular complexes or simplices, right? We're not gonna talk about, what am I saying? Cellular simplices? Cellular complexes. We're not talking about things called delta complexes. This is thanks to Eilenberg. So delta complexes. So we're now employing a delta complex structure. So delta complex is to remind us of the fact we're still trying to put cells inside here, but this time we're considering identifications of those cells in here, right? So this time, instead of having 4 separate, 0 cells, we have only one. Because notice how if I try to identify the red arrows, so this here and this here, I would get a cylinder. And these points over here collapse to a single pair of points. So this becomes that and that. And then now I have my green arrows. And then once I identify those, these 2 vertices become 1 vertex in the torus. So it becomes 1. And then I have that the green arrows run this way, and then the red arrows goes that way in the torus. All right. And we'll see later that when we try to find the second homology group, it's actually 2 copies of my, or it's actually the direct sum of my coefficient group with itself, because there are 2 two-dimensional holes here, right? So, okay. So, what do we do with this? So first thing we ought to do is consider the fact that we're identifying these edges and these faces. So this face is the same as this face. This edge is the same as this edge. This edge is the same as this edge. And all these points are the same point. So I'm just going to label them with one singular, label, So I'm going to consider these vertices as points X, 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 X. This here is A, B, and then C. And I don't need to label the other ones because they're the same thing. So really, we're only considering 1 0 cell, 1 cells, and 1 cell. So, I mean, if you guys want to, you guys can list that down so you don't get confused and bogged down in the computation of these things. So, because now we have a 2 simplex here, we now have to consider 3 coefficient groups, or 3 chains. So, I have 0, C3, no, 2, I mean 2, for the faces. C1, and then C0. And then back to trivial. And then I have my corresponding maps del 3, del 2, del 1, del 0. And again, trivial, del 3 is the same as del 0, and then just 0. That's their image. Now what we do. Okay, so let's consider this fact now. Like last time, I think I already discussed, I discussed about, yeah, 3 simplices. So I was trying to compute the homology group of a disk. So recall from then that faces gets mapped onto their boundaries, right? So of course, that's why it's called the boundary map, because we're considering what are they mapped onto, right? So what exactly is their boundary? With these maps, we're trying to identify what the boundaries are and putting those into a free abelian group. So for our 2 chains, of course, we only have one face, so it's only generated by one element, which is just that face, which I'm going to call A. So 0 is mapped onto the free abelian group on A, and then A is mapped onto its 3 edges. So it's the finite, the free abelian group generated by A, B, and C, because A, B, and C bounds A, B, C, and I'm just erase these things so that it doesn't get too laggy. Okay, oops. Okay, let's erase that. Okay. All right, so A, B, C, and then that free abelian group is mapped onto what? What is it mapped onto? It's mapped onto a single point X, or at least a free abelian group generated by a single point X, and then that's set to 0. Of course, my boundary maps del 3, del 2, del 1, del 0. And this crucial fact that del 3 is equal to del 0, which is trivial. Now, the reason why that fact is not stated outright, because the usual definition of homology is very general, wherein they consider up to n, n simplices that's embedded into your space. So they don't state right off the fact that a certain del 3 equals del 0 equals 0, but that's what happens, right? When you restrict it to only a certain dimension of simplices you embed into your space. But of course, the higher dimension the simplices works, but of course the dimension stays strictly below the dimension of your topological space. The more, or the higher dimension gets for your simplices, the easier your computation gets. So in this case, if I decided to try to, somehow approximate this with a bunch of infinite little 1 cells, that's gonna make my computation much, much harder. So instead, I'm just gonna embed a 2 cell into here. So you guys will notice that this is the same as del 3 of just one copy of our coefficient group, and that's mapped by del 2 to G direct sum G direct sum G, and it's mapped onto just one copy of itself once again. And 0, del 0, del 1. All right, so now let's find out our boundary maps. So obviously, right off the bat, you guys will know that del of A is precisely A plus B plus C. So all the edges. So it's a linear combination of all the edges. And next, you guys will notice then that, of course, according to my orientation, excuse me, some construction going on, so just excuse the noise. Excuse the noise, there's construction going on. All right, so del of A, so A is mapped onto, well, it's really X. So all of these guys are mapped onto X. Oh wait, yeah, del B is X, del of C is X. So there's that. But things will change once we try to find the kernels, right? So let's begin our computation. So let's start with the zeroth homology of T2. Of course, again, usual procedure, that's the kernel of del 0 mod the image of del 1. And the kernel of del 0, del 0 maps is this map over here. And we're trying to find linear, yeah. So what is the kernel of del 0? Oh no, I'm not trying to find linear combinations here. It's simply the entire group. So that's G mod the image of del 1. So what's the image of del 1? So the image of del 1 is precisely 0. It's a trivial group. So that's just isomorphic to G. And that shows because T2 is a path-connected space of only one component. So it's really just one copy of your coefficient group. Okay. Next, let's compute the first homology group of T2. So H1 of T2. So it's the kernel of del 1 mod the image del 2. So the image of del 2, of course, is A plus B plus C. So it's the finite abelian group generated by that sum, A plus B plus C. And then the kernel of del 1 is each of these guys. So A plus B plus C. No, actually, the kernel of del 1 is the entire thing. Because X can be interpreted as the 0 group, right? So it can be interpreted as 0. And you notice that no matter what linear combination of A, B, and C we do, it's all sent to X anyway. So we can interpret that as being sent to 0. Though it's not, X is not strictly, or no. So the free abelian group is not generally isomorphic to 0, the 0 group, but it's still generated by one element, right? So you can think of it as 0. So basically, the entire thing here, this entire group is the kernel. So essentially, that's the free abelian group generated by A, B, and C. And this is a free abelian group of one generator. This is a free abelian group of 3 generators. So you guys can probably see where this is going. This is G, direct sum G, direct sum G. And then this is just isomorphic to G, so that's G. And that's isomorphic to G, direct sum G. And this checks out when you, with the trivial examples you usually get in algebraic topology textbooks. If you replace G with the integers, that's precisely Z mod Z, or Z direct sum Z. Okay. And that's true because we have 2 one-dimensional holes here. The one-dimensional holes being the hole that's encompassed by this red circle, and the one that's encompassed by this green circle. This green circle over here. So it's precisely 2. There are 2 one-dimensional holes here. Alright, so our computation is not done yet. Because we have a 2 cell here, it reaches up to H2. So H2 of T2. So of course, again, kernel del 2 mod image del 3. And the kernel of del 2 is, well, precisely G, because there's only one batch of elements there that are sent to the trivial part, or to 0 in G, you know, direct sum G, direct sum G, and that's just G itself. So it's G. And a mod the image of del 3. So what's the image of del 3? That's just 0. Because, you know, we're just sending the 0 group into our group generated by A, which is G. So there really isn't any other elements that 0 is sent to other than itself. So that's the image. It's just the 0 group. and then that's just G. And notice that throughout the entire thing, each of these groups I'm modding out by or quotienting out by are normal subgroups. Now, I'm not going to prove that just now, but I want you guys to prove that as like an exercise, that each of these groups that we've been quotienting by are normal subgroups. And so they evenly distribute or they evenly quotient out our original group into cosets. Right? So that's just isomorphic to G. And then that's it. We're done with our computation. For H3, of course, we don't have 3 cells here. All right? There's no 3 cells in the identification space. So that stuff is gone. It's out of here. So 3 cells. So it's just... So for H3 and above, our homology group vanishes. So in general, HK of T2, our torus, is Z, or no, G, for K equals 0, and for K equals 2. So it's obvious there is one two-dimensional hole here, which is the two-dimensional hole here is not, surprisingly, it's not this hole that I drew an arrow through. It's this entire space inside the torus. So a bit wacky. It's not we're defining holes not in the usual sense that's common to the layman, but we're in fact like, it's absurd because the entire two-dimensional hole is this over here. A bunch of spheres we embed into here. This space inside the torus. It's not the hole that you guys think, right? That's outside the torus. But you guys can think of it that way, I suppose. So, yeah. There are 2 ways to interpret the two-dimensional hole inside the torus. One is the actual hole that I drew an arrow through, and then one is this space inside the torus. The entire space inside the torus. Okay. And so there's G mod G for K equals 1, and trivial group for K that's neither of those. So it's greater than or equal to 3. And so again, the reason why it's G direct sum G is because there are 2 one-dimensional holes. The one-dimensional hole encompassed by the red circle that goes around the latitude of the torus, and then there's one that goes along the meridian of the torus, or the longitude of the torus, this entire space here. So those are the holes, the one-dimensional holes. Okay, so that's for the torus. Of course, forgot the femboization of it. So F HK of T2 with coefficients in G. The G is a femboized group, okay? So I'm not gonna write it as but I'm gonna write it here anyway, FG. So the femboization of it. So we're not considering just regular numbers that represent the equivalence classes of my curves, my homotopic curves that shrink to a point. But now we're talking about femboys, right? So K equals 0 to, and then this is FG mod, or mod, I mean direct sum FG for K equals 1, and then it's the trivial femboy group for K greater than or equal to 3. So, oh wait, forgot this, F. So there's for the torus. Now how about for the sphere? Now the sphere has a relatively more simpler computation. And there's only one two-dimensional hole inside it, which is the space inside it. So let's compute that. Before we end today's lecture, let's compute the homology group of FSN. Oh no, FS2, sorry. I'm going to reserve the computation for the homology groups of FSN to when we discuss about the excision theorem. And that's way, way down the line of lectures. So right now, let's focus on FS2. The thing I'm writing on my tablet keeps fucking, it keeps falling. Keeps tripping from its slot in its case. This is a case that keeps this inclined so that it's easier for me to write. And it just keeps falling. Because I have to keep it upright so it doesn't fall. Alright. Okay, so let's discuss the homology group, or let's compute the homology group of FS2. So originally it's just a circle. I know it looks like a rock, but just think of it as a circle. It's the same thing anyway. Okay, so we now think of it as two triangles. And then we glue them along the boundaries. So it's a bit hard to visualize it, but think of it as like, I guess it goes this way, and then it's like, I don't know, it curves a bit. So I'm gonna draw a base triangle so it's easier for you guys to see or visualize. So like this, and I'm gonna break it up. Okay, and then I'm gonna draw these guys. So this is the top triangle, and then this is the bottom triangle. I don't know if this is the correct sort of visualization for it, but you guys can see that when I glue this edge, this edge, this edge, this edge, this edge with this edge, I would get this entire thing. So there's that. That's the visualization for the gluing procedure. So again, we're considering a delta complex because we're identifying things together. Because cell complexes are for, regular triangles. Okay. So we're identifying this edge, we're identifying this edge and this edge. We're identifying this edge and this edge. So when we're drawing arrows or these tick marks to indicate stuff, they serve a double purpose. They not only tell us the orientation of each of these two cells, but they also tell me where I identify these two cells. To what parts of each other do I identify these things? Where do I glue them? That's the thing, or that's what we do. All right. So you guys may be thinking, okay, right now we have what? 2 copies of a triangle. So that means I have 2 faces, 6 vertices, 6 edges. So but the thing is, we're identifying these things. So we're only considering one of them. So we only have to compute the homology of one of these things. So it really reduces to computing the homology of a 2-cell. But we have to take into consideration these identifications as well. So it's not as easy as you think it is. Again, let's label these things: X, Y, Z, A, B, C, X, Y, Z, A, B, and C. And then I'll label the faces A and B, capital A and capital B. So now, instead of just one map, we're considering 2 maps now. And this time, C2 is generated by 2 elements. So the 2 chain is now generated by 2 elements. So it's a free group on 2 elements. Or free group generated by 2 generators. Or free group on 2 generators. So it's generated by A and B. This maps onto the one generated by A, B, and C. And this maps onto the fab generated by X, Y, and Z. And then that's mapped as 0. 0, 1, 2. And again, you guys can see that this one here is a direct sum of our coefficient group with itself. This one's a direct sum with itself 3 times, and same thing here. Now, it doesn't matter if this is isomorphic to this one here. Okay. So let's compute the boundary maps. So the boundary maps of A and B, they're separate things. They're 2 separate things. So A and B. So A is precisely A plus B plus C. And because A and B are the same thing, that's also the boundary of B. So the image is really a free abelian group generated by 1 element only, which is A plus B plus C. Okay, so next, the boundary map of each of these edges according to our orientation. So del A is Y minus X. Del B is z minus y, and del c is x minus z. So those are boundary maps for these guys. And of course, all of these guys, del x, del y, del z, are all, they all map to 0. Of course, according to our image. So again, the crucial fact, del 3 is the same as del 0. It's the same, it's just 0. That's their image, essentially. Okay, so I mean, you guys can see right off the bat, because the image of del 3 is 0, that the third homology group is trivial, right? So yeah, there's that. There's a hint, or sort of thing that you can compute right off the bat if you don't feel like computing from the starting from the 0th homology group. So let's start with the 0th homology group. So and then let's start. All right. So wait, no, S2. And then we'll Femboy as the space later. Okay. So that's again the usual procedure: kernel, del 0, mod, image, del 1. So the kernel of del 0 is the entire group x, y, z, mod the image of del 1. So what's the image of del 1? The image of del 1 is, it's the trivial group again. So it's a group generated by 0, which is the 0 group. And there's really nothing here except 0 that's sent to 0. Notice that the boundary maps of these guys, so each of these elements are sent to the respective x minus, or the respective linear combination or elements in here. So really none of these guys, none of these generators gets sent to 0. But of course 0 exists inside this free abelian group because we need an identity, right? So it's only 0 that's sent to, that's really the image of 0, of del 0, or del 1 in this case. All right, so that is just isomorphic to the direct sum of G with itself 3 times. Oh wait, no. No, just 1. Sorry. And that is not x, y, z. I was wrong there. It's x plus y plus z. There. So that's just G. Okay. H1 of S2, same procedure. Again, kernel, del 1, mod, image, del 2. And, okay, we have to think about this a bit. So what's the kernel of del 1? So we have to think of formal linear combinations such that it would equal 0 of A, B, and C. So the image of A, B, and C, the addition of the images of A, B, and C, and I attach some coefficients from G, capital G, and then I equate those to 0 to find the kernel. So here comes the boring part again. So I'll consider alpha times A plus beta times B plus gamma times C equals 0. And of course, the corresponding images are y minus x plus beta of x minus y plus gamma of x minus z. It's equal to 0. And then again, gathering things together, we have that gamma minus alpha x, and then alpha minus beta times y plus beta plus gamma, beta minus gamma times z equals 0. And of course, each of this relation only holds when alpha equals beta equals gamma. And we do the same procedure as we did with the torus and mod out by the equivalence that of mod out by that equivalence. So delta equals gamma, beta equals alpha. And so we end up with the free abelian group generated by x plus y plus c. That's our kernel. Mod the image of del 2. So what's the image of del 2? The image of del 2 is one that's spanned by essentially A, B, and C. Right? A plus B plus C. So yeah, that's the image of del 2. You can see here. So that's A plus B plus C. And then you see that it's trivial because we have only one generator, one generator. Okay, what's H2? H2 is different this time because this time we have a two-dimensional hole inside it. There is no one-dimensional hole here. There are no one-dimensional holes here, right? I mean, I could put one here, a circle, but the thing is, this surface is solid. I mean, the inside may not be solid, but the surface is solid. So when I put a circle there, or any loop, right? It doesn't matter, I can just homotope those guys together. There is always an area inside here, so that hole is closed. But there is a two-dimensional hole here, which is this area inside the sphere. Or that shape that this circle is a cross-section of. Or the ball, at least. Because zero-dimensional holes are zero-dimensional holes. One-dimensional holes are like the area bounded by a one-dimensional surface. Two-dimensional holes are volumes, basically, essentially. So that's why I said the two-dimensional hole in a torus is the area inside it, or the volume inside it, or the space inside it. Okay, so H2 of T2 is now the kernel of del 2 mod the image del 1. And the kernel of del 2 is whatever is sent to A, B, and C. That's just A minus B. And then that's the image of del 3, of course, is 0 because by this here. And then that's just our coefficient group G. And that makes sense because there is one two-dimensional hole here because that's the volume here. If I had two spheres and then I wedge sum them together, right? I have two spheres meeting at a single point. I have two path components, obviously. But this time I have two-dimensional holes here. So, of course, the homology group would change. Not only because it's an entirely different space, it's two spheres for God's sakes, but because we now have two holes inside them. So really, for the dimension, so let's say that K equals the dimension of our space X, then the kth homology group of our space X is some tuple of our coefficient group. Some n tuple of our coefficient group, where n is the amount of k dimensional holes in X, right? So the torus is a two-dimensional surface. There is only one two-dimensional hole inside it. Now here, this is the same thing. Now, the only reason I said there's technically two of them is because I can interpret it as the one that's inside the surface and the one that's in the middle of the surface. All right, so to wrap up this lecture, HK of T2 is defined piecewise as it is 0. For K equals 0, it's G. And also for 2. So for K equals 0 and 2. And then it's trivial for K not equal to 0 and 2. So that's for S2. S2, not T2. And the corresponding femboyized one is FHK of FS2. That's just a femboyization of this group, of our coefficient group. Now the reason why, okay, before I leave, the reason why I wanted to generalize this to a abelian group G is that I want you guys to run free and not just confine yourselves to defining the coefficient group as just the integers. Don't restrict yourself to the integers. Get crazy with these coefficient groups. Go nuts. You guys can use the real numbers. You guys can use the octonions. For God's sakes, you guys can use the Sedenions. So do it. In fact, I did the crazy, and when I tried to define the coefficient group of the homology of the n sphere, I used the real numbers. So there's that. So go crazy with the coefficient groups. And so that'll end this lecture.